Hello there and welcome. In this video we're going to focus in on vapor pressure lowering using Raoult's law. You should already know how to calculate a molar mass using the periodic table and your calculator, and definitely you should know how to calculate the mole fraction in a mixture, and we'll go over that. All right, so first of all, Raoult here on the very left, back in the late 1800s, studied the boiling vapor pressure, a lot of different stuff actually, but he studied vapor pressure of pure water versus solutions, and he found that the vapor pressure of salt water, for example, is ever so slightly less than the vapor pressure of pure water. And there is a diagram here kind of showing how water is inhibited in terms of forming a vapor. Perhaps the sodium chloride or whatever solute molecules are dissolved here in blue are kind of retaining or holding the water molecules from escaping the surface, probably through hydrogen bonding or dipole-dipole interactions or ion-dipole interactions. Now, what is Raoult's law? Very simply, it is this equation here. Let me take it through each of these letters. So the pressure of the pure component A is PA, and that's usually water. We're mostly working with water in the lab, so if we have pure water or we have salt water, it's the water we're talking about, okay? So this is the pressure of component A, the vapor pressure. Now look, seriously, if you have salt water, salt is not evaporating, right? It's the water that is evaporating because the water has vapor pressure. Sodium chloride is a non-volatile solute. It's dissolved in the water, but it doesn't volatilize, okay? Chi, remember that Greek letter, we're just going to show it as an X here, is the mole fraction of water, okay? So we're focusing in on the water. You want to calculate the mole fraction of water in a mixture of salt water or sugar water, something like that. And PA with this little star thing is the pressure of pure water, and that comes from a steam table. The steam table is located in table 9.2 of the OpenStax chemistry textbook. I'll provide a link in the description below. Make sure you have a steam table handy. Some professors will ask you a question, hey, what's the vapor pressure? But they'll never tell you what the pressure of pure water is at that temperature, so you've got to consult the steam table. Here's an example. Okay, we've got a solution containing 5.00 grams of urea. This chemical formula is provided, and they tell us it's non-volatile, so that makes the calculation very easy. We have 0.100 kilograms of water. We have some vapor pressure of pure water, and we want to know, hey, what is the vapor pressure of the solution? We, of course, always assume ideal behavior, and the laws hold up, all right? So step one, you want to calculate the moles of urea. So carbon, oxygen, nitrogen, hydrogen, multiply them all out, add them all up, and you get the molar mass of 60.0553, okay? Now what you want to do is convert grams to moles by dividing by the molar mass. And please follow along, do this on your calculator and make sure you get the same number. I'm always going to round it to 3 significant figures because we're starting with 3 significant figures. Step 2, you want to calculate the moles of water. So we got 0.100 kilograms. That's equivalent to multiply by 1,000. Yes, 100 grams. And then we divide by the molar mass, 18.015, and you get 5.55 moles of water. Okay. Step 3 is to calculate the total moles. And remember, the total moles is equal to the moles of water plus the moles of our non-volatile solute. Okay. In this case, remember, it doesn't break up to form ions. It's just one thing there. So it's a total of 5.63 moles. All right. Now here's the meat and potatoes. We're basically trying to calculate the mole fraction, X or chi if you want to call it that. And that's the moles of water divided by the total moles. Okay, so it's 5.55 divided by 5.63. And we don't make a percent out of this. We just leave it as a decimal. It's 0.986. Okay, so of course, in this solution, it's mostly water. Okay. So we're going to use that number later on. Keep that in mind. Now what we want to do is calculate the vapor pressure, okay? So what you need to do here is use the formula, okay? The pressure is going to be equal to the mole fraction times the pressure, all right? So the pressure is equal to the mole fraction, which we calculated before, 0.986, times the pure pressure. I'm calling it the pure pressure, okay? And that's given to us in the word problem or the steam table. You could Google that. At 25 degrees C, what is the pressure of water? You're going to get 23.7 torr or 23.7 millimeters of mercury. So we're plugging that in there, and we get a value of 23.4 millimeters of mercury. What amazes me is that Raoult, back in the late 1800s, had sensitive enough equipment to measure a pressure change of 23.7 to 23.4 millimeters. That's like 0.3 millimeters. I mean, grab a ruler and look how much is 0.3 millimeters, and you've got to have very keen eyesight to be able to see a difference in the mercury level of just that little. So it's amazing. He was a very good experimentalist to make the measurements, make the law, study all this stuff, and now we call it Raoult's law. Good for him. Here's the summary of steps. So if you're studying, I suggest you write these down. You're going to calculate the moles of solute, the moles of solvent, calculate the total moles. Eventually, the goal here is to calculate the mole fraction of water. Okay, it's the water part that we're interested in. And then you calculate the pressure of water. Again, it's the water vapor, right, that we're calculating the pressure of. And it's going to be equal to the mole fraction times the pure pressure. Okay? That was brief, but if you want to see other practice problems, please check my channel. I have a lot of worked problems in there, and it does take practice. I don't expect students to see this once and get it. It takes a while to just go through practice problem after practice problem after practice problem to eventually get mastery at this. Thanks for watching. Please like, please subscribe. Have a great day, everybody.